So yes, indeed, I will talk about Pytmosph3R, which is a tool to generate the transmission and emission spectra from 3D, for example, GCM simulations. So the problem with GCM simulations is that they are actually very expensive in terms of computations. And so to remedy to this problem, people use low resolution correlated K opacity data to generate the simulation. And we can compute afterwards through a transmission spectrum with a higher resolution in terms of spectral resolution with, for example, Pytmosph3R. So it's a post-processing tool after computing a simulation of an atmospheric model. So as an input, you have the atmospheric simulation and also the light rays, meaning that you can, for example, change the orientation of the light rays, meaning that you change the observer around the simulation. So you compute first the optical depth of each ray that you can then integrate into a transmittance map. So that's an example here on the right of GCM simulation of WASP121b, seen from the observer point of view. And below you have the transmittance map that is computed by Pytmosph3R, meaning that well, the dark means that it's opaque, and yellow means that the light goes through, which can then be integrated into here transmission spectrum on the top right. If you want to see a bit more of the exact equation that we use, I put them here, but otherwise I think I will just move on. So why use a 3D model instead of just a 1D model? What's the motivation behind the Pytmosph3R is that there has been some studies that have shown a lot of biases from 1D models, especially in hotter planets, in ultra-hot Jupiters, for example. So there is a series of papers by Aurélien Falco showing, for example, that you can retrieve the wrong C/O ratio due to the differences of temperature between the day and the night in the simulation. So what is Pytmosph3R capable of? It can compute in the public version the transmission spectra and emission spectra. It can also include, as I said, rotation, meaning that you can, for example, study a transit over time, so that you can study how the spectrum will look like at the ingress or at the egress. And we have shown in a paper last year that we can see indeed the variations due to the asymmetries of the simulation when the planet rotates during transit. Pytmosph3R also has many routines for visualization. You can, for example, on the bottom left here, see a transmittance map associated to a map of aerosols. So you can clearly see that the repartition of the aerosols here is blocking the light on this part of the transmittance map. You can also here see an evolution of a simulation over time. So it's the same simulation at two time steps of the simulation, and you can see that the clouds are actually moving over around the limb. Then on the right, you have here just a simple visualization of the temperature map, following a cut in altitude or latitude and longitude, for example. I will not demonstrate today how Pytmosph3R works, but there is a tutorial online at this link. I can put it in the Slack afterwards. There is also a video I will show later. I just wanted to say that in this tutorial, we will start by downloading some data that is here the block commented. But actually, if you have opacity data from another software like petit code, petit radtrans or Torex, for example. All these formats are supported natively by Pytmosph3R because it's relying on ExoK, which is a code developed by Jérémy Lecomte, which can convert opacity data from one format to the other, etc. And also includes a 1D atmospheric model. So yeah, if you have one of these opacity data, I strongly encourage you to just use this data instead of just the examples that we provide that is kind of just for the tutorial. Then in the tutorial, you will go through some elements like setting up your atmospheric parameters, the planet, etc., where the observer is located in the system. And then you will plot the spectrum, etc. In the tutorial, you will see, you will first start with a simple 1D example, but it's, well, kind of not what is the point of Pytmosph3R. So you will have some other examples in more complex geometries like 2D and 3D with some transmission and emission. And actually, I wanted to point out that there is a video on the EMAC channel on Pytmosph3R that I just discovered last week. In this video, I just want to mention that in the beginning, you will have a lot of introduction on the compilation part. So we have solved the issues that were shown in the video, so probably the installation part should be much faster now. Not any bugs, hopefully. So yes, you can accelerate the installation part probably. And I just want also to mention that there will be, hopefully soon enough, an upcoming release with a few changes to the API, but not so much, but also including other modes like phase and light curves. Also including the winds and Doppler shift. And so there will be some changes to the examples, but it should not be too much. And I will leave you on just some links to install Pytmosph3R, so hopefully this command should work natively. I think you just need maybe to have a numpy installed, but otherwise I will stop here and see if you have some questions.
Awesome, thanks a lot, Aurélien. So I see we have a question. So we had a question in the chat that I copied over to Slack, which is from Sukrit Ranjan. Who says, could you give some insight regarding the differences between 1D and 3D modeling? What are the magnitudes of the error induced? What are the physical origins of these errors? So that's kind of a large scope for the question, but I don't know if you have like some.
No, actually, I don't have much. I don't think I have a lot of slides on this, unfortunately, but clearly the biases come just from the fact that we sample over the limbs very different temperatures. Actually, if you have the 1D assumption like this, you will just sample one temperature, while in a 3D, you will actually sample over the ray of light here a large range of temperatures. So yes, in the retrieval, you will probably just retrieve what the atmosphere would look like at the terminator, while in fact what you want to do is to model all of this path, all of this array. Not sure if that's enough as an explanation.
I don't know, maybe if there's some more detail that the person wants, you can discuss more on Slack.
Okay.
Yeah, thanks a lot. I think it's a really nice tool, and I've experienced myself the kind of hurdle of having to deal with different standard outputs from different standard GCM codes and kind of trying to process all that. My question was going to be about phase curves, but since that's in your upcoming release, I don't know how big of an effect that is, but do you take into account the different like effective size of the planet as it goes around the star because like a part of it is kind of blown up, or is it just like from the temperature? Like, do you take into account the different extent of the atmosphere that you're seeing?
Yes, for sure. I
Like
think
kind of what you're showing on this schematic here. Like if you're seeing the planet from a different
that's
angle.
the day side is much more, indeed, should be larger than the night side, you mean?
Yeah, okay. But my question was whether that was taken into account in the phase curve calculation, the kind of size difference and not just the temperature over the whole
In
line of
emission in emission mode, you mean? Like
yeah, for the thermal phase curve, let's say. But that would be the same, I guess, for
actually, I think indeed, I'm not sure we take much of the height scale into account. Probably we.
I don't know if that's a big effect or not. I'm really just asking out of.
I might have to check the code on this, but I think indeed we just take the radius of the planet as a reference.
Okay, that's awesome. Thanks a lot, Aurélien.